Oh man, this is actually a lot more tough. A lot more difficult than I thought it was going to be. What the hell? Good morning, everybody. You guys, well, it's not really morning. I completely forgot to, I don't know my mic. I had such a mess this morning.
Is this even... What mic is this using?
I really hope I have audio. Otherwise, this is going to be an interesting bit. Anyways, what was I saying? Such a mess. It's such a mess. What was I? So I woke up still at the same time. I woke up around 6. But instead of turning on the camera, I was hoping I'd be able to just quickly ship out or just send out yesterday's vlog. I completely forgot to give an update last night before I went to bed, so that was hilarious. And the vlog, I just ended up getting distracted and sitting there watching YouTube videos, Instagram, and sitting on Facebook. So 2 hours of my morning gone. But at least I scheduled out all the content for today, and I will, hopefully you guys see it. Like, comment, share, give me some feedback. Share your thoughts with me. You know when I'm not doing well, what I am doing well, just so I can improve and I can get better. But today, my friends, we will be working on, actually let me pull it up. I did my lives and I didn't know exactly what I was working on, so I was kind of just guessing, but let me get you exactly what we'll do. I have a fly in here, it's pissing me off, so. Where'd it go? Give me 2 seconds. You're fine. You're fine. Okay, so that took a lot longer than what I expected. But at least now we have an AI that can reasonably play at least 4x4 tic-tac-toe, and it plays it in a pretty quick manner. So yeah, I'm pretty happy. It has a pretty decent win rate. So we're pretty much at this point done with the search algorithm portion of this. Now we get to move on to some more exciting things. Now let's move on to Q learning. Yeah, so I mean, for just a little bit of context before we get into here, I completely skipped over the whole how I actually implemented this AI portion, because that was all done behind the scenes and that was done off camera. That was done, I think, on my own time. The reason being is because it took a lot of effort, a lot of research to actually get it to that point. So where we left off in the last episode was the Minimax that I coded. It wasn't able to play 4x4. It wasn't able to play efficiently on the 4x4 tic-tac-toe grid, and it would take way too long to make a move, which makes sense because what it's doing is it's trying to go through all the possible states. In a 3x3 tic-tac-toe game, there's about like 200,000 or so possible states, so it can do that. But in a 4x4, you quickly get into like the millions of possible states, and so it takes way too long to evaluate millions and millions of states, because again, it's going through each and every single possibility. In a 4x4, there's so many different variations of how the game can go. Whereas in a 3x3, it's a fairly small sample size. So what I had to do is I had to go and research ways to optimize, ways to make it run faster and things like that. And I think I have footage. So let me just pull up some of the footage that I have, and I'll kind of just go through. So this first one here is so Negamax is an algorithm that I found on Wikipedia, and so I went ahead and I implemented the algorithm, just the pseudocode that I found on the Wikipedia page. To be honest, kind of annoyed because I spent so much time trying to implement it, and everything was on Wikipedia. If only I checked Wikipedia before I did it, I could probably gonna save myself so much time and headache, but whatever. So anyway, I went and I copied the Negamax algorithm from Wikipedia, implemented it, but it wasn't working well. And so that's, I wasted so much time trying to figure out why it wasn't working and trying to fix it, yada, yada, yada. Then afterwards,
it did start to work, but what I wanted to do is I wanted to make it even faster. And so there's something called a transpositional table. And so a transpositional table, what it does is basically, rather than the AI having to reevaluate the same game states all over again, because, yes, there are a ton of states that it will have to take a look at, but some of them will be the same, right? So it's like, if like in a 3x3 tic-tac-toe game, if the game starts with X going at the top corner, O going in the middle corner, and then X going in the bottom corner, it's the exact same thing. Or so X O X. You reach that exact same state if X goes in the bottom corner first, and then O goes in the center, and then X goes in the top corner, right? And so, but the way vanilla Minimax, or the way the vanilla search algorithm will treat that, is that they're two completely separate states, and so it will evaluate both states. And so to save time, you're like, no, this is the same game board. You've already seen this before. You've already done the evaluation for this. So how about you just save this information in a table somewhere? And so when you see this exact same game board again, you just go to that table and you just figure out what it is, or you just pull up the information that you were already able to find. And so that's what a transpositional table is. Now, I didn't implement it correctly the first time. And so what would happen is, because I was trying to save text, the transpositional table would get way too large, the game would crash, and that was a whole nother issue I had to figure out. So I got into like memory management a little bit, but then to solve it, because memory management was taking a while, so then to solve it, what I tried to do is I tried to implement hashing. And so the hashing, essentially what it is it's just, it's representing text, or more specifically representing like a game state. So for example, Zobrist hashing is something that's used in chess a lot. So all it is it's just representing a game state in bits, so like zeros and ones. And so it's doing it in a way, numbers, which then translates to zeros and ones. And it's doing it in a way where each game state or each board position each game state is unique. And so you can never have, if you can come up with different algorithms, but what you'll find a lot is that there may be a point in time where two completely different game states evaluate to the same number, right? So let's say you want to, for example, for each game state, you want to, you can try working it out on your own, because I'm just giving, this is supposed to be quick commentary, but I've went way too long. So essentially with the hashing algorithms, what it tries to do is that every game state has a very unique code or very unique number that it evaluates to prevent collisions, as they're called, right? And so that's something I had to learn and had to implement from scratch as well. And so Zobrist hashing was something that I had to that I was implementing, and something that I implemented off camera. And so it worked really, really well. And so in the clip, you'll see that Negamax is going against Naive, and it's working, i.e., like Naive should never be able to beat Search, because Search plays a perfect game. A perfect game for Search either results in a win or a draw. There's no way you can ever lose. And so, you can see that it's working. You see it's working pretty well, and it's much faster, especially in the beginning where it has to evaluate everything. And so, that's that. So that's all the stuff that happened behind the scenes. So just giving some context as to how we got to where we are. And without further ado, let's get back into the Q-learning portion of the video.
Q-learning is part of the reinforcement learning, which basically just means that we're going to have an agent, which is our AI bot, play the game and then learn through various different algorithms. Now, it just so happens to be Q-learning. Q-learning is basically like our AI acting like Curious George, in a sense, in that it'll find itself in a state such as this one, and then it will just start playing around, and it'll say, hey, well, what happens if I go here? And then eventually what it'll do is it'll start to learn, if a game board looks like this and I play here, usually I end up losing. And so I don't want to lose, because if it wins, we give it a good reward in terms of, discipline. Yeah, no, let's not call it discipline. Let's just say that if it wins, we're going to give it good, yummy numbers to munch on. And if it loses, we're going to give it bad, disgusting numbers to munch on. So the Q learning algorithm always wants to win, because when it does, it gets to munch, it gets to have a really good dinner. And if it loses, sorry, man, I'm gonna have to give you this terrible dish. It's because you lost. It's your fault, not mine. If you don't finish it, that's your dinner for tonight. If you don't finish it and you go to bed, you're just going to start where you finished off tomorrow morning. And that's just that. Yeah. Okay, so coding a Q-learning agent is quite simple. I believe, though, that we're going to quickly run into the same issue we ran into with search, in that getting a basic Q learning algorithm is going to be very simple. It's going to be very quick. However, I do not think that so basically our Curious George or our Q learning agent will have to play through a whole bunch of different states, and then I'll have to memorize and I'll have to start to remember all these different states. Now, again, remember, in normal tic-tac-toe, there's about 20,000 states. In 3D tic-tac-toe, it's just impossible for our AI to be able to remember all these states. So we're probably going to have to end up evolving him from just normal Q to something called deep Q. So yeah, we're probably going to evolve him from Q to DQ. Okay, so let's just get started and implement a very basic Q learning agent within our 3x3 tic-tac-toe game. I'm actually also just going to clean up a little bit, since we're now done with a whole bunch of these things. Move all these guys there. Okay, that should definitely clean things up a lot more. And then I'm just going to call this normal. Okay, everything's clean and all looks good. Okay. And let's get rid of these guys. Let's go back to the normal 3x3 grid. And let us get started on creating our Q learning AI. Okay. Nope, we're gonna actually keep it up there because I want it to persist even after we're kind of done. So we're pretty much just going to use what formula is this thing called again? So yeah, we're pretty much just going to be using the Bellman equation, which basically just says that, you know, the reward that you get for going from a state, from taking an action and going to the next state, is the reward of that state or of said state, plus the maximum reward of the future states that you can get. So if you can win, you win. If you can lose, then it's going to be a 0. If you can win, it'll be perhaps a 1, or I don't know what let's just say a 1 for now. And if you lose, it'll be a -1. And so essentially what the AI will start to do is it will start to learn, okay, if you take this step, it usually leads down this path that ends up losing, and so it will start to, on its own, start avoiding such paths. So how the heck did I hash? How did I hash you? Oh, probably shouldn't, but I'm just gonna copy these. Just gonna copy. Just gonna do I need a Zolfist hash for this? Yeah, I probably do, huh? Okay. No, because well, let's just see what happens. Okay. that should be it. Let's just test it out and see how it goes. I guess that worked. Okay. 281. Okay. Oh man, I need a quick break. My brain is fried. Okay. Let's try to finish this up and then go to bed. Oh man, this is actually a lot more tough. A lot more difficult than I thought it was going to be. What the hell? Okay, so Q learning is pretty much done. All we have to do now is just let it train. After it trains, we're going to have it go up against naive AI. So in order to be able to do that, I'm going to have it just save for now. It's just going to do its thing for overnight. And in the morning, I'm just going to have it go up against naive AI and see what happens. See what interesting tactics it has picked up. They share the same table. So yeah, should be good. Because they share the same table. What did I just witness? That was the lamest game ever. Holy. So now that that is done, to be able to save, all that really matters. What I call it? Save Q table. Okay, that's why. That's why I get set twice. Yeah, we only need one. Let's just test it out. See what happens. Yeah, those should not be 0.75. That was a little odd to me. Okay, let's see what happens. Okay, this is not going to go anywhere interesting. Oh my god, don't tell me to. Oh, this is too painful to watch. Okay. Oh, please tell me you're gonna make. Holy cow. Okay, so none of them made a good move. So now the Q table should at least reflect. Okay. And yep, it reflects it perfectly. So now what I'm gonna do is I'm gonna keep that, exit out of here. What I'm going to do is, yeah, I think we can now load the Q table. And let's just run that overnight and see what happens. Let me just refresh XXO, XX blank, blank O. Yeah, you run X blank O, XX blank. Blank, oh. Yeah, if you make a boneheaded move like that, you're gonna lose it. Okay. Now let's just speed things up, have them play a couple of games, and we should be good. So the last thing I'm gonna have to do is actually just X1. Okay, you know what? This is not gonna work. Yeah, this is already massive. Holy. So I'm unfortunately going to have to let me play without seeing what's going on under the hood. Okay, I'm kind of curious to see what it is actually under the hood right now. Alright, well, continue learning. I'll see you tomorrow.